In this lecture, we'll explore how urban microclimate functions and how planting strategies, especially tree and vegetation-based approaches, can significantly improve thermal comfort, reduce heat stress, and enhance urban resilience. This is the content of today's lecture. The aim of this lecture is to understand how urban vegetation affects microclimate. Research has proven that urban vegetation is significant in mitigating the heat island effect and improving human health. You will be able to identify planting strategies to improve comfort and reduce heat. The urban tree configuration, especially vegetation, is a critical landscape element that actively cools the environment through evaporation and transpiration. And you will have basic knowledge about species selection, canopy design, and spatial configuration. Integrating microclimate considerations ensures that landscape designs are environmentally responsive, energy efficient, and comfortable for people. Key goals in sustainable urban design. Evidence-based climate-responsive design knowledge can assist designers with addressing the challenges they face and with developing better-informed design solutions. Urban microclimate refers to the local climate conditions created by the built environment. Factors like building form, surface materials, vegetation, and human activity all shape temperature, humidity, and wind in cities. The urban microclimate influences how we feel in a place and how much it will be used. Comfortable temperatures encourage walking and cycling, social interaction, use of parks, plazas, and outdoor dining. Extreme temperatures, hot or cold, reduce outdoor presence and can make some areas feel unsafe or abandoned. Urban heat islands occur because cities absorb and store more heat than natural areas. Temperatures in cities can be several degrees higher, especially at night, leading to increased discomfort, energy demand, and health risks. Cities in hot arid climates are particularly vulnerable to extreme heat, especially during summer. Effective planning requires diagnostics. Tools like GIS mapping, remote sensing, and CFD modeling identify heat hotspots and simulate airflow. These help designers select the most impactful planting strategies. Microclimate can be described by several main factors. Measuring urban microclimates involves capturing air temperature, surface temperature, humidity, and wind speed. Data can be gathered from fixed meteorological stations or in situ field measurements. Satellite and airborne sensors for land surface temperature and albedo are used in a broader context. We will look at each factor in more detail. Air temperature is closely linked to human thermal comfort. In cities, high temperatures make people feel overheated, fatigued, and uncomfortable. Low temperatures can reduce motivation to be outside and increase vulnerability to cold stress. Air temperature sets the baseline for comfort levels. The air temperature in the urban environment is measured near the ground surface. Cities are warmer than rural areas due to heat absorption and retention by buildings and roads. Vegetation cover has a direct connection to air temperature. Trees and plants cool the air through shading and evapotranspiration. Surface materials concrete, asphalt, and dark roofs store and release heat, increasing air temperature. Urban form also influences air temperature. Dense buildings reduce wind flow and trap heat. Surface temperature is the temperature of urban surfaces, roads, roofs, pavements, etc. It is influenced by albedo. Albedo is the measure of a surface's reflectivity, how much sunlight is reflected rather than absorbed. Albedo ranges from 0, absorbs all radiation, to 1, reflects all radiation. Light-colored or reflective surfaces, e.g., white roofs and concrete, have high albedo, reflect more solar energy and help reduce heat storage, lowering urban heat island intensity. Dark surfaces, e.g., asphalt, dark soil, have low albedo and absorb more solar radiation, raising surface temperature. Vegetation reduces surface temperature. Green spaces have lower surface temperatures due to shading and transpiration. Materials store the heat at different rates and amounts. A high thermal mass surface warms up slowly and cools down slowly. Conductivity affects how surfaces store and emit heat. A high thermally conductive, material reacts quickly to changes in air temperature, quick to warm, quick to cool. Cities can develop localized hot zones, hot spots, where materials and geometry concentrate heat. Humidity is the amount of moisture in the air. It is influenced by evapotranspiration. Vegetation increases humidity by releasing water vapor. It reduces air temperature and helps balance urban humidity levels. Using vegetation is the most effective and natural method. Paved and impervious surfaces reduce evaporation, often leading to drier air locally. Water bodies, urban lakes, fountains, can locally increase humidity and cool nearby areas. Water introduces humidity as it evaporates. Even small features can change the local microclimate. A controlled mist system can safely raise humidity without excessive water use. Wind speed is the rate of air movement through the urban area. It is influenced by urban form. Tall buildings and narrow streets can block or channel wind, creating urban canyons. Dense building clusters trap solar radiation because there are fewer open spaces for heat to dissipate. Building surfaces, concrete, asphalt, glass, absorb and store heat during the day, then release it slowly at night, keeping the area warmer. Narrow streets and high-rise buildings reduce sky exposure, limiting nighttime cooling through radiation. Less airflow also means pollutants and humidity accumulate, worsening air quality and discomfort. Vegetation and trees can act as windbreaks, reducing wind speed but improving comfort and reducing dust. Surface roughness and more structures increase turbulence and disrupt airflow. Understanding local wind directions helps create comfortable outdoor spaces, reduce wind tunnels, and improve ventilation. Vegetation, especially trees, contributes to urban cooling and improved microclimate through several mechanisms. Trees significantly enhance urban microclimates and cooling through shading, evapotranspiration, and windbreaking. By shading surfaces, particularly low albedo materials such as asphalt, trees significantly reduce heat absorption and effectively cool the area. Trees also cool the air through evaporation and transpiration. Furthermore, trees help maintain cooler temperatures and higher humidity by shading the soil, reducing evaporation of ground moisture. Additionally, by altering wind patterns and reducing speed, trees can enhance air cooling. In other contexts, optimal tree locations can channel breezes into urban areas, thereby augmenting cooling. The turbulence caused by wind interacting with tree canopies results in enhanced evaporation and transpiration rates, contributing to enhanced cooling. They contribute to perceived noise reduction. The high filtering capacity of air pollutants and the dust binding capacity of urban trees benefit humans and animals. Green infrastructure is the most effective adaptive strategy to limit urban heat and thermal discomfort. Trees, edges, grasses, potted plants, climbing plants, private gardens, parks, or lined-up urban trees, including green roofs and vertical gardens, are the ways in which vegetation can be found in urban areas. Urban squares and open street spaces can only be used in the summer months if there is sufficient shade. Green elements are usually preferable for creating shade. Artificial man-made shading devices, such as parasols, canopies, pergolas, and panels, can be used when underground infrastructure prevents planting. Using materials with both high albedo and emissivity can cool urban surfaces during the day, but designers must also consider factors like wind and shade, which can strongly influence thermal comfort and lessen the importance of material properties. Urbanization increases impermeable surfaces. Permeable pavements and depaving restore evaporative cooling, lowering surface temperatures and improving mean radiant temperature. They also help with stormwater storage and runoff reduction. Factors such as function, service life, usage properties, and costs, as well as ecological sustainability, are decisive for the choice of surface material. Not only production itself but also long-distance transport can negatively affect the energy balance. Local and regional materials should be used in preference. Water cools cities mainly by evaporation and evapotranspiration, which reduce air and surface temperatures. Moist soils, vegetation, and open water bodies moderate heat. Water also influences humidity, supports shading vegetation, and can create local breezes. all of which shape the urban microclimate and help mitigate the urban heat island effect. Water mist nozzles can be strategically placed to improve the local microclimate. A strong planting strategy looks holistically at species selection, canopy design, spatial placement, and material combinations. A good strategy also considers seasonal performance and irrigation needs. Tree benefits depend on species, building height, and the distance between the tree and the building. Poor placement can block winter solar gains, reducing building energy efficiency. Shading pavement in parking lots and streets effectively cools communities. Trees should be planted along the perimeters and in medians of parking lots, or along the length of streets. Integrate with buildings to optimize facade shading and wind flow. Strategically placed shade trees can also benefit playgrounds, schoolyards, ball fields, and similar open spaces. Create continuous green corridors to enhance cooling airflow. Increase tree spacing density in heat-exposed zones. To maximize their cooling effects, it is essential to strategically position the trees in optimal locations. Trees are not the only vegetation option. There are many areas where trees either do not fit or grow too slowly to be effective over the short term, in which case vines may work better. Vines need less soil as well. Vegetation on a green roof shades surfaces and cools the air through evapotranspiration. Thus, the optimal vegetation configuration depends on wind direction, vegetation combinations, tree types, planting intervals, and climatic characteristics. Evergreen trees exhibit stronger thermal optimization than deciduous trees in both winter and summer. Effective urban microclimate design uses mixed deciduous evergreen plantings to balance summer shading and winter solar access while ensuring year-round cooling. Mixing both types enhances cooling by approximately 0.5 degrees Celsius compared with single-type plantings. Species selection depends on the country and region, and no precise advice can be given for all places. Crown density, expressed by leaf area index, LI, and leaf area density, LAD, is central. Denser crowns block more radiation and increase shading, though overly dense canopies can trap heat in compact canyons. Canopy size and tree height strongly influence cooling. Taller or broader crowns provide deeper shadows and greater evapotranspiration, though they may reduce nighttime heat release if canopy ventilation is low. Leaf morphology affects albedo, radiation blockage, and transpiration. Deciduous trees with thin, broad leaves achieve higher transpiration rates, while evergreen needles have thicker, waxy surfaces that reduce stomatal opening and lower transpiration. Selecting species with high transpiration capacity and low stomatal resistance maximizes cooling where water availability permits. Broad, continuous tree canopies provide the strongest cooling because they maximize radiation blockage and latent heat flux, especially when leaf area index LI and leaf area density LAD are high. Dense, wide crowns of deciduous species such as Tilia cordata and Quercus robur offer substantial daytime shading and high transpiration in summer, effectively reducing pedestrian-level air temperature. Their seasonal leaf loss allows valuable winter solar access, preventing excessive winter shading and supporting passive heating. Multi-layered vegetation, combining understory shrubs, mid-story trees, and upper canopies, improves shading efficiency by intercepting sunlight at multiple heights and enhancing evapotranspiration. Studies show that mixed height or mixed species plantings increase cooling by producing three-dimensional shade and improve thermal comfort compared to single-layer canopies. Strategic layering also supports more effective air movement and reduces heat storage. When continuous canopies are used in open urban forms, cooling efficacy increases further due to improved ventilation and canopy space. Green roofs play a major role in improving urban microclimates and reducing the urban heat island effect. By adding vegetation and moisture to the rooftop, they can lower surface temperatures by 20 to 40 degrees Celsius and reduce the surrounding air temperature by 1 to 3 degrees. They also reduce the heat entering buildings by up to 60%, significantly cutting cooling demand. Beyond temperature regulation, green roofs provide important hydrological and atmospheric benefits. They retain between 50 and 80% of rainfall, helping with stormwater management while boosting evaporative cooling. They also filter particulate matter and create small habitat patches that help strengthen ecological connectivity across the city. There are three main system types: extensive roofs, which are lightweight and efficient; intensive roofs, which support deeper vegetation and have high ecological value; and semi-intensive systems that sit between the two. Their performance depends on factors such as substrate depth, moisture availability, plant species characteristics, and roof albedo, insulation, and thermal inertia. In hotter arid climates, irrigation becomes essential. Finally, green roofs perform best when integrated with other cooling strategies, such as cool roofs, green walls, permeable pavements, and urban microclimate modeling tools. Combining design strategies, vegetation, materials, shading structures, and water elements offers the strongest cooling potential for urban spaces, especially in hot, arid climates. Trees provide shade but block ventilation. In contrast, grass is suitable for nighttime cooling effects, but cannot provide daytime shade. The best solution is to combine trees with grass. Still, this does not sufficiently account for the seasonal changes in thermal comfort. The combination of a water basin and tree shade is effective. Another effective combination is trees and buildings. The presence of vegetation and parasols can provide shade and improve thermal comfort. Using high albedo materials and vegetation together can reduce air temperature more than either strategy alone. Overall, the design strategies suggested in the literature primarily focused on the summer season, given its extreme heat and drought. However, the diurnal and seasonal effects of climate-responsive design strategies remain unclear and warrant further investigation. Integrated solutions, such as combining photovoltaic canopies with other measures, which have been addressed in some initial studies, as well as interventions to prevent stormwater damage and store water, require more attention. Also, lessons could be learned from vernacular design in hot, arid desert climates, which has the potential to successfully address local climatic challenges and contribute to thermal comfort and energy savings. However, these lessons should be further investigated and carefully transferred into contemporary urban open spaces. When we talk about effective urban cooling, the strategies themselves are only half the story. Successful implementation depends on strong policy frameworks. Cities need long-term support systems such as urban forestry programs that ensure consistent planting, maintenance, and canopy expansion over time. Design guidelines and zoning regulations can require developers to integrate shade trees, permeable surfaces, and climate-responsive planting into new projects. Incentive programs, like rebates for cool roofing materials or funding for street trees, help accelerate adoption across private properties as well. Another important direction is linking greening with stormwater management. Stormwater integrated planting systems allow cities to manage runoff while creating cooler, more comfortable public spaces at the same time. These policies ensure that cooling strategies scale up from isolated interventions to entire neighborhoods or districts. At the same time, community-based green interventions play a vital role. Initiatives such as Green Streets show how resident-driven planting can transform streetscapes, improving microclimate conditions while strengthening social cohesion. These bottom-up approaches are especially powerful in dense urban areas where available space is limited. Together, coordinated policy and community action create the conditions for lasting, citywide climate resilience. Researchers Ken Tominga, João Cortesão and Michiel Bax present a conceptual framework for using convivial green streets (CG) as a resource for climate adaptation. When applied consistently, CG can become an emerging green practice with a positive impact on urban adaptation to climate change. It may provide localized climate amelioration that supports social engagement outdoors. They argue that making convivial green streets operational in climate-responsive urban design can be achieved by 1. Informing inhabitants on how their informal, spontaneous, and ad hoc interventions on the streetscape can boost conviviality and the climate responsiveness of cities. Private initiative can play a vital role in the climate adaptation of our living environments. However, People are mostly unaware of this, and conventional top-down approaches to city making often prevent it. 2. Informing urban designers and other early adopters on how to incorporate CG into a design schema without, however, imposing any deterministic procedure or design solution on local populations. Designers can integrate CG into their design schemas while ensuring internal and external coherence. Planting design and green infrastructure play a critical role in improving urban microclimates and combating the urban heat island (UHI) effect. Strategically placed vegetation, such as parks, urban forests, and green roofs, enhances comfort, boosts resilience, and supports long-term climate adaptation by cooling cities through shade and evapotranspiration. When combined with reflective materials, water-based cooling systems, and thoughtful urban planning that promotes natural airflow, these measures significantly lower ambient temperatures, reduce energy demand, and improve air quality and biodiversity. As climate change and rapid urbanization intensify heat challenges, context-aware planting and integrated cooling strategies are essential for creating healthier, more livable, and economically resilient cities.